So, students, I hope you are fine. And now let us take the same discussion that we have been discussing on these gas-filled chambers as detectors. And what we'll be talking about here is ionization chamber. And if I rightly go back, we have this behavior in different regions of applied voltage, and and to be precise here, this region, the region 2 that we have, uh, is called as its ionization chamber. Uh, uh, it's the region of ionization chamber. So, so to say, and what we have is we have taken some crude diagram for gas-filled for gas-filled ionization. So when this detector that we have is when it operates in the region 2 of the graph that we have talked about, this region, it certainly collects the actual number of ions produced because the recombination in this region is small. It's negligible. So the count rate that it records has actual ionization current produced without any multiplication of ions. So we have ionization current in this region. And the pulse height so produced that we have here in case of pulse ionization chamber, the pulse height uh, is of the order of 10 to the power of minus 4 volts. This is for alpha particles that we have here. For alpha particles, it's 10 to the power of minus 4 for alpha or beta particles who have the energies of the order of 1 mega electron volt. So to say that as we have small number of ions produced, which are collected instantaneously, the counter remains dead. It remains dead. You can see that there is a saturation in this region. It remains dead, inoperative, for a time of about 1 millisecond between the two successive counts, and its energy resolution is of the order of 1/2%. And the ionization chamber does not give the count of individual particles. What it does is it gives us the average effect. It gives us average effect of large number of particles. So, so to move on from here, let's go with another detector that we have, and we call it a proportional counter. And this proportional counter, it works in proportional region that we have. So let's talk about proportional counter. And we have region 3 here, and this region 3 is the proportional counter. Now the point is that when a particle of some low specific ionization passes through the ionization chamber that we talked about, the pulse produced is very small. And it's very small to be detected independently. So potential difference is increased so that it works in proportional region, in which the size of the output signal is proportional to the number of ions that have been formed by the primary ionization process. When these foreign particles have entered into the chamber, they have caused ionization. So the proportional counter basically it has a resemblance. So to make it like that, it has a resemblance of the like of this. What it does, it contains a cylindrical gas-filled tube with a very thin central wire, and this central wire is insulated from the tube, and the central wire is always made positive in this case, and with respect to the metallic cylinder, which is made negative. And and the point that I'm trying to tell here is that this metallic cylinder tube, it serves as a collecting electrode which is connected to a pulse amplifier, and the tube is filled. The tube that we have, it's filled with methane and approximately 20% of argon. So it has methane, CH4, and nearly 20% of argon gas. So the first to improve the stability, and the first one that's the methane, it improves the stability, and the second is this 20% of argon that we have. It raises the amplification factor. Now, what is the amplification factor? Is basically the number of ion pairs formed by the collision as each electron travels towards this central wire. And this is what is called as multiplication factor or gas amplification factor. So multiplication factor depends on the anode radius. Okay, so we have this anode, and it depends on its radius and the radius of the cathode. So voltage, it certainly does depend on the voltage that you are applying, because the voltage should fall in the region of proportional region of the curve that we have discussed, and the pressure inside the gas. Now, if I assume that we have a potential difference V that we apply across the anode wire of radius, and it has a radius, suppose this wire has a radius equal to A, and cylindrical cathode that's surrounding it of radius B. So this is the radius of wire in the diagram, and this is the radius of the spherical cylinder that's out there is B. So certainly there is electric field. So we have electric field in cylinder, and that electric field can be written as V by R log to the base E B by A. So this will be the magnitude of electric field that will be set up between the electrode, the positively charged central cylindrical wire, and the negatively charged the cylindrical shield. Now, the point is, if we have a charged particle, and this charged particle is incident on such a detector, and it produces an ion pair along the trajectory that it has, okay? So there is an ion pair, so positive will go towards this, and the negative will go towards this. And the voltage at that point is, say, 1000 volts. And B is nearly 1 centimeter, and A is nearly 1 millimeter, right? So the field strength at the central wire can be calculated. So we can have this electric field that will be 1000 by 1000 by R log to the base of that is 1 centimeter by 1 millimeter. So the value that we get here is nearly 6.7 times 10 to the power of 6 volts per meter. So this much of electric field is set up between the two electrodes inside the proportional counter. Now, the ion pairs produced are accelerated through such high electrical field. So they have to they will be passing through with a very, very high acceleration. And because the magnitude of electric field is very high, and this is what causes gas multiplication. So this is what causes the secondary ions inside the chamber, and the electrodes collect the respective negative and positive ions. They will collect them, and the total ionization current produce a pulse through the resistor, and you have the pulse that's produced along this resistor. So to say is, as the height of this pulse that's registered through the amplifiers, the height of this pulse is proportional to the energy of the incident particle that has entered the chamber. So it can be used to estimate the energy of the particle, and the number of particles incident per unit time, or the intensity, can be estimated from the number of pulses produced per unit time. Okay.